In this lesson, we are going to learn how to define isomer, as well as start to look at the isomeric relationship between a pair of molecules. The basic definition of an isomer is that it has the same chemical formula, but a different arrangement or connectivity of the atoms. Let's look at some examples. For the molecule given at the top, we see it has 6 carbon atoms. We can then add hydrogen atoms so that every carbon has 4 bonds. Remember, these are our implied hydrogens. So when we add those in, we see that we have 14 hydrogens. So we get a chemical formula of C6H14. Notice this is a chemical formula and not a condensed structure. Chemical formulas give us the total number of each type of atom, where a condensed structure gives us something that shows the connectivity of those atoms. When we go to the molecule on the second row on the left, we also see that it has 6 carbon atoms. We can add in our hydrogens so that every carbon has 4 bonds, and we will see we also have 14 hydrogens. The molecule in the middle has 6 carbons, as well as 14 hydrogen atoms. The molecule on the right also has 6 carbons and 14 hydrogen atoms. Notice that all of these have different connectivity of the atoms. In the molecule at the top, we see all the carbons in one chain. The bottom 3 molecules show branching. The 2 on the right show one group branched to the side. The molecule on the left shows 2 groups branched to the side. Since they all have the same chemical formula, all of these molecules are considered isomers. Let's look at 2 pairs of molecules to determine if they are isomers or the same molecule. You have to be careful in the way the molecules are drawn to determine the difference between the two. So in each pair of molecules, we see that we have the formula C6H14, so we know there's some kind of a relationship between each pair. When I look at the first molecule on the left, I'm going to number the main chain of molecules 1, 2, 3, 4, 5. I'm going to do the same for the molecule on the right. What I notice is that the group that's off to the side, the CH3 group, in the molecule on the left is attached to carbon 2, and in the molecule on the right, it's attached to carbon 3. Now, we also have to look to see, is this just an effect of the way the molecule is drawn, or are they truly isomers of one another? So we're going to number the molecule on the left in the reverse order. So we're starting on the right side and numbering it 1, 2, 3, 4, 5. Notice that we don't switch the order of the molecule on the right. So when you're doing this comparison, you only switch the ordering of one of the molecules. So if we look at the numbering in purple on the molecule on the left, we see that we could call the side group at carbon 4. And so regardless of how we number it, we see that the side group of CH3 is either at carbon 2 or carbon 4, which is very clearly different than the molecule on the right where the CH3 group is on carbon 3. Now let's look at the second example. Again, I'm going to number the carbon atoms in the main chain on both molecules. When I look at the molecule on the left, I see that the CH3 group is on carbon 2. It's on carbon 4 in the molecule on the right. I'm now going to reverse the order of numbering in the molecule on the left. And what I see is that the CH3 group is on carbon 4 in the molecule on the left, and it's on carbon 4 in the molecule on the right. And this tells me that these 2 molecules are exactly the same. They're simply a mirror image of one another. So these are the same molecule. They're not considered isomers. Let's look at another set of molecules. All of these molecules are isomers of one another, even though they look very different. We want to explore some of the differences that can occur between pairs of isomers. If I look at these 2 molecules, what I see is that we have a COC bonding versus the COH, so we can have our oxygens in different places in a molecule. We can have the double bond in a different place, so the location of the double bond can result in an isomer. The location of the OH group. In the molecule on the lower left, what we see is that it's attached at the end of the chain of carbons. On the molecule in the upper right, we see that it's attached in the middle of the chain of carbon atoms. We can also see that we can have a chain compound versus a ring compound. As long as the chemical formula is the same, it's still considered an isomer. We also see the location of a substituent group, which is just a side group, relative to the position of the oxygen. Notice that the CH3 group in one molecule is directly across from the oxygen, and in the other molecule it's at the carbon immediately next to the oxygen. All of these are examples of the different ways that we can have isomers of molecules. If you look through all the molecules, you will see that they each have 4 carbons, 8 hydrogens, and 1 oxygen. So we get a chemical formula of C4H8O. Are these two molecules isomers of one another? First, we'll count the number of carbon atoms. So we get 5 carbons. Then we can go back and add our hydrogens, and so that every carbon has 4 bonds, and we get C5H12 for the top molecule. For the bottom molecule, we also have 5 carbons. We add in our hydrogen atoms, and we see that we only have 10 hydrogen atoms. So these molecules are not isomers because they have different chemical formulas. Are these molecules isomers? Again, we need to find the chemical formula of both, and we get C5. Adding in our hydrogens, we have 12 hydrogens for the top molecule. On the bottom, we have 5 carbon atoms. So we have C5. Each carbon is going to have 2 bonds to hydrogen, and so we get C5H10. So these molecules are not isomers because they have a different chemical formula. Are these molecules isomers? We count the carbons on the top molecule and we get C5. Adding in our hydrogens so that every carbon has 4 bonds, we get 10 hydrogens. On the bottom we have 5 carbons and 2 hydrogens on every carbon to give us 4 bonds for each, gives us H10. So these molecules are isomers because they have the same chemical formula of C5H10. Are these molecules isomers? So we're going to count our carbon atoms. So in the molecule on the left we have 6 carbons. We're going to add in our hydrogen atoms so that every carbon has 4 bonds, and we get H8, and then we also have 1 oxygen atom. We're going to do the same thing for the molecule on the right. We're going to count our carbons, and we find that we have 6 carbon atoms. We then add in our hydrogen atoms and find that we have 8 hydrogen atoms and we have 1 oxygen atom. So these two molecules are isomers because they have the same chemical formula, C6H8O.